Welcome to Chapter 7, Section 1, Slope Fields and Euler's Method, brought to you by my awesome Hovercam Solo 8 and these tremendous Signo Uniball pens. Best pen for the money you can get. Okay, definition. Slope fields, pretty interesting. We're not going to talk about this a lot as far as application, but we're going to show you how to build slope fields. Euler's method, that's the correct pronunciation. We're not even going to discuss in 7.1, but we will be discussing it later on. So we start off with the definition, differential equation. Well, this makes pretty much sense. An equation involving a derivative is called a differential equation. The order of the differential equation is the order of the highest derivative involved in the equation. Perhaps we have a third derivative, would be order 3. Okay, slope field or direction field. When we're in calculus, once we're just completely literal in calculus, we might just think of things in terms of dy dx. But dy dx is to calculus as blank is to algebra. Well, dy dx is change of y over change of x. This is just slope. So this says our slope is a function of xy. That is just that's our direction field, but we'll refer to that as a slope field. And you'll see, we will build those, and you'll see it's pretty easy, a little bit tedious, but it's a plot of short line segments that just represent possible slopes at individual points x, y. It's really, really simple to build, just tedious. Okay, up until this point, we've been dealing with defined integrals, where we would have a value here, say 0, and a value here, say 3. So we would say the area of f of x dx from 0 to 3. Well, an indefinite one, we aren't defined here. So typically where we would say, let's say we had the integral of x squared dx, and normally we would have that maybe from 0 to 5 or something, but we would say, well, I got to start with an x cubed, but the derivative of x cubed is x squared, so I've got to divide by 3, and then we would put our values in that are here and here, subtract, put the top value in, minus, put the bottom value in. And that's basically our integral value, possibly our area under the curve, depending on zeros along the way. Well, we know that works because the derivative of this gets me back to there. But so does the derivative of x cubed on 3 plus 7, or x cubed on 3 plus any constant. And this is what we need to do when we're asked for like a general integral or an indefinite integral, because that could be, that value just gets absorbed when we take the derivative process, and this still gets us back to x squared. Hope that makes sense. Properties of indefinite integrals. I don't think we have to spend a whole lot of time trying to memorize these. They are exactly what we want them to be. Let's say we're dealing with sine of x. Our f of x is sine of x. And let's say k is 3. Doesn't this make sense? If I have 3 times sine of x, I would say, how does that looks just like sine of x, except you would hopefully say 3 times as tall. Well, if a function is 3 times as tall, shouldn't the area under its curve be 3 times as great? If instead of my sine of x function looking like this, it now looks like this, and this is 3 times as tall. If you think about all those rectangles we build in here versus the rectangles down here, and every rectangle is 3 times as tall, then my area would be 3 times as much. So therefore, we can take a constant multiplier from within an integral, pull it out, just like we'd hope we could. And therefore, if k is -1, we can pull negatives out. That's just a special case that we'll use a lot. And what we would hope for our sum and difference rule would be the sum of a function plus a function. The integral of the sum of a function plus a function would be the integral of the first plus the integral of the second, and it is. Likewise for minus. So no big deal memorizing those. Then they just have a big list of things we ought to already know. Now, perhaps we never drew this connection yet, but if we were finding the integral of, let's say, x to the 5th dx, how we've been talking about that, I would have said, well, if I start thinking in terms of derivative instead of integral, I would need an x to the 6th. Well, that gives me 6x to the 5th, so I'd need to, forget about that mark, I'd need to cancel that 6. We'll take a look at this rule. X to the n, add 1 to the exponent, and divide by that same exponent. Oh, add 1 to 5 and divide 6 and divide by that 6. So there we go. Hopefully, if we think of this thing as integral 1 on x dx, that is screaming ln to us. E to the, well, the derivative of e to the kx is e to the kx times k, so we need to cancel the k. Notice every one of these plus c, they're indefinite. I don't have starting points, end points. They're indefinite. Let's take a look at this. What's the derivative of cosine of kx? It's negative sine of kx times k. Cancel the negative, cancel the k. There we go. So these are things we should be aware of. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared, so account for the negative. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent, so account for the negative. And all of these are just kind of in a parallel universe where we're going from derivatives, kind of the way I talked back through here. So nothing earth-shattering on that page. All right, find the general solution. Anytime they're asked for a solution to a differential, we want to get back to plain old y equals. So this would be y equals. To get rid of this, I would have to antiderive this. So my antiderivative here, to end up with an x to the fourth, I have to start with an x to the fifth. The derivative of that is 5x to the fourth. We're in luck. The derivative of tangent gets me to secant squared, so if I put tangent x here, that gets me positive secant squared. Account for that minus. And plus c. Boy, it'd be an easy way to lose a point or two every single problem if we forget those plus c's there. Notice the derivative of this with that plus c in there still gets me here. So we could, in effect, take this curve, whatever x to the fifth minus tangent x is, and we could raise it or lower it by a factor of c, and all the slopes are the same. Doesn't that make sense? Go back to my sine function that I was talking about. If I truly drew this over here, it's the same curve, and I put it straight up, aren't all the slopes at all the same x values the same? So it doesn't matter how high, how low the graph is. That's all that c does to it. It raises and lowers a graph, and we add something on to the end. Okay, so y equals the derivative that gets me sine, derivative of cosine gets me sine, but the derivative of cosine is negative sine, account for the negative. Well, e to the derivative of e to the is e to the times the inside function. The inside function here is negative 1, so the negative's already accounted for. This is actually plus. Derivative of e to the negative x is e to the negative x times negative 1. And I would need an x to the fourth to end up with an x cubed. Derivative of x to the fourth is 4x squared. I want 8 of those, so adjust. Plus c. Nothing to it. Now, we'll see this from time to time. The derivative of 5x, or 5 to the x, I like to say it wants to act just like e to the. And e to the x is e to the x. So this wants to be 5 to the x, but because it's not e, we compensate for that with inverse e to the, ln, 5. So I look at this and I say, oh, if the derivative of this is that, the integral of this should be just 5x, or 5 to the x. So y equals 5 to the x. This one. We've seen it a number of times now in my first calculus class session of the day. I think I had about 6 or 7 people raise their hand. They're starting to recognize this one. This is tangent inverse x plus c, the easy to forget plus c. All right, this next problem is sneaky. I don't know derivative of what gets me this mess. But I look at this, and it's no coincidence, this t to the third. If I just treated that as x, oh, by the way, this should be dt here. If I just treated this as x, then, and I, hold that thought. If I took the derivative of cosine, I would get sine of t cubed times 3t squared. It's no coincidence that this is the derivative of t cubed. It makes this manageable. So the derivative of what gets me to cosine, sine of, would have to be t cubed, but the derivative of this would be cosine t cubed times 3t squared. We got it. Y equals this plus c. This would be a really good time to pause this one because this is almost the same problem. You can try it if you'd like. Okay, I'm going to go. The derivative that gets me to secant squared is tangent. It has to be of x to the fifth. I'm just hoping that this works out. Times the inside derivative of x to the fifth times 5x to the fourth. We've got it. Y equals this plus c. Okay, moving right along. Solve the initial value problem explicitly, exactly. Well, it's like what we were doing. What we were just doing, we'd do this. We'd say, well, y equals, the derivative of cosine gets me the sine, but the derivative of cosine doesn't include the 3. I'm going to add it. And the derivative of cosine includes a negative, so I need to cancel that. And this would be plus c. But now, this says y is 2 when x is 0. So 2 equals, well, the cosine graph looks like this. We all know that. And cosine of 0 is the peak. That's 1. So this is negative 3 times 1 plus c. Add 3 to the other side. C is 5. Final answer, y equals negative 3 cosine of x plus c, but c is 5. My crease here. Okay, good time for you to try B and C. That's what I did in class, and we had a lot of success on that. I'm going to go ahead, so if you want to pause, pause now. To take a derivative and end up with x to the 6th, I would have started with x to the 7th. The derivative of that is 7x to the 6th. To take a derivative and end up with x to the 2nd, I need to start with x to the 3rd. The derivative of that is 3x squared, but isn't negative. Take a derivative and end up with 5. That's plus 5x plus c. Oh, by the way, this should be u equals. I think I did that in class today, too. All right, u is 1, u because of this. U is 1 when x is 1. So 1 to the 7th minus 1 to the 3rd plus 5 times 1 plus c. Cancel, subtract 5. c is negative 4. So final answer, I did it again. U equals x to the 7th minus x to the 3rd plus 5x plus negative 4 or minus 4. Excuse me. Okay. If I think of this as negative x to the negative 2nd minus 3x to the negative 4th plus 12. That might help us. You may be fine without that, but I'm going to go ahead and add that for right now. If I end up with a negative 2nd, I must have started with a negative 1st. The derivative of x to the negative 1st is negative 1 x to the negative 2nd. Got it. To end up with a negative, or to end up with an x to the negative 4th, I must have started with an x to the negative 3rd. If I take the derivative of that, I get negative 3 x to the negative 4th. Got it. So that's actually a plus there. And I would have had to start with 12x here. Plus c, that's what y is. Integrate both sides. Okay, so y is 3 when x is 1. They're being pretty merciful here. 1 to the negative 1st plus 1 to the negative 3rd plus 12 times 1, 12. Plus c, that's 14, or c is subtract 14, negative 11. Final answer, I'm going to put it back in this form. Y equals negative 1 on x squared minus 3 on x to the 4th plus, oh, I'm looking at the wrong row. My fault. I bet you caught that. Y equals 1 on x plus 1 on x cubed plus 12x, getting that from here, minus 11. Final answer after a little miscue. Okay, let's continue on here. Same thing. Do we recognize this? I hope we recognize this now. Y equals integral that gets me this special guy right here. By the way, this should be a t. Would be tangent inverse of t. 2 to the, punishing the 2. Okay, I'm getting this now, plus 2 to the. If I take the derivative of this, I need 2 to the t, but it's not an e, so punish the 2, ln 2, plus c. Y is 3 when t is 0. Now the graph of tangent, I remember it looks like this, between pi on 2 and negative pi on 2. And this isn't saying what is tangent of 0, it's saying when is the tangent's height 0. The tangent's height 0 is 0 at 0. So we get 3 equals 0 plus, careful, 1 plus c. C is 2. Final answer, y equals tangent inverse t plus 2 to the t plus 2. Okay. Y equals, well, the derivative of secant is secant tangent. But it's not times 4, so we adjust for that. Plus the derivative of e to the t is e to the t. To end up with a plain old t, I must have started with a t squared. That gives me 2t, but I want 6 of them. Plus c. V, oh, this is V equals, did that earlier too, V, when t is, all right, so V is 5, 4 times secant of 0 plus e to the 0 plus 3 times t to the 0, 0 to the second plus c. Made a mess out of that. 5 equals, well, cosine of 0, just talked about it, cosine of 0 is 1. The reciprocal of 1 is 1, so this is 4 times 1 plus 1. 3 times 0 squared is 0 plus c. So c, subtract 5 on both sides, is 0. So our final answer, V is 4 secant t plus e to the t plus 3t squared plus 0. Alrighty. Solve the initial value problem using the fundamental theorem of calculus. Now, it's telling us they're going to have definite integral. It will contain a definite integral, a defined integral. Therefore, they're basically telling us this. Hey, maybe it's not going to be easy to find the antiderivative of sine x squared. You can think about that for a minute. Now, if I go integral sine x squared dx, and I say that's what y is. Now, this is the big key. When x is 1, so I'm going to run from something up to x. We end up with a y value of 5. I'm just going to put in a here, just for thinking through this. We're going to run from some value a to some value x. So when x is 1, y is 5. Now, I could choose a lot of values for a here, but if I choose a to be 1, what is this integral when x is 1? When x is 1, this is the integral of sine from 1 to 1. It has no width, therefore this is 0. So now when x is 1, by putting a 1 down there, I've zeroed this out, and it says 5 equals 0, when I put 1 in here, plus c. Oh, c is 5. So I could go straight to here once I understand this. Y is the integral 1 to x, sine of x squared in here, dx plus 5. Now, I do think it's worth understanding this, but once we understand this, makes this pretty easy. I don't know what the integral of e to the cosine, the integral of e to the cosine is e to the cosine, but then it's times negative sine. I don't know how to cancel negative sine of x. So I'm going to say this is just the integral e to the cosine of x dx. This is saying when x is 2, the y value is 9, so when x is 2, it's not like I'm really thinking about putting the 2 here. I'm thinking about putting the 2 in here for x, and what would zero this out? Start at 2. So this becomes 0. So I get y equals this plus C, but when x is 2, this is 0, so 9 equals C. 9 equals, I zeroed this out at 2, 0 plus C, so C is 9. So there is our final answer on this. Okay, and here we go, slope fields. First one, really, really easy. Construct a slope field for different differential equations. In each case, copy the graph at the right. Now, we've done this for us. And draw tiny segments through the 12 lattice points, 12 of those in each case, to show the slope of the graph. So this just says the slope is x. So at the point 1, 2, I'm not going to draw this out for everyone. At the point 1, 2, the slope is 1. It's x. So slope of 1. Notice I got a target at that. It's right there. Slope is 1. You don't have to draw the little target dots in there. Now right here at the point 1, 1, x is still 1. And at 1, 0, x is still 1. And at 1, negative 1, x is still 1. And x is the slope. That's allowing me to move my curve up or down. Okay. Now at 0, 0, x is 0. Slope 0. X is 0 here, slope 0, x is 0, slope 0, x is 0, slope 0. And all of these points contain an x value of negative 1, so they all have slope negative 1, and we just try to draw that as accurately as we can. Now, let's think about this for a minute. This would integrate, if I integrate both sides, I get y equals x squared on 2 plus c. Well, take a look. My curve is wanting to look like this. This is showing the curving, how the slope is changing. It's flat here. Well, that looks kind of like it could be x squared on 2 plus c. Now, doesn't mean it would go through the point 1 on 1. It actually goes through the point here. It's flat, but it starts trying to become that slope in there. Okay? And that's more of a study for later on, how we fit it. Now, what if C was 1.8? We'd be up in here, and we know we're flat. And then we know by the time we get to here, we want to have a slope that would be matching that. Okay? That's kind of where we're headed with this. We're just not there yet. We're just building these. So I'm going to put B up here. dy dx is 2x plus y. And you may want to chart this. You may want to create a t-chart. You may want to do something like this. Say, here's my xy, here's dy dx, then we've got, for instance, the point 0, 0. When I put in 0, 0, I get 0, 0, 0. But we might be able to do these in your head as well. Let's start up here. At 1, 2, I'm not going to write that down for everyone again, but we're going to go through this one. I get 2 and 2, 4. So a slope of 4 would be aiming clear down here. Really steep. Just kind of trying to visualize that aiming down here. How about at 1, 1? I get 2 times 1, 2, plus 1, 3. Slope of 3. It's trying to aim down over 1, down 3. It's trying to aim down at this. How about at 1, 0? I get 1 here, 0 there. I get 2. It's trying to aim down there. And how about 1, negative 1? That would be 2 minus 1. It's trying to aim at that point. It's almost like a focal point here for us. Okay, how about at 0, 2? Put in 0 for x, 2 for y, I get 2. Slope of positive 2. Aiming right down here. 0, 1, slope of 1. How about 0, negative 1, slope of negative 1? Excuse me. Got a bit of a cold today. How about negative 1, negative 2? Negative 1 would be negative 2, and negative 2, negative 4. Oh, spring is here. How about negative 1, 1? Ooh, this is, wait. I'm sorry. Negative 1, 2 up here would be negative 1. That would be negative 2 plus 2. This is actually 0 up here. I'm sorry. I bet you caught that one too. How about negative 1, 1? That would be negative 2 plus 1, negative 1. Aiming down there. How about negative 1, 0 would be negative 2. Aiming steeper. And how about negative 1, negative 1, negative 2 and negative 1? That would be our negative 3, aiming steeper yet. Okay, so one little glitch here. All right, good time for you to try the third one, part C. That's x minus 2y. So we've got dy dx equals x minus 2y. You might want to pause this, see if we end up in agreement on what our graphs look like. Okay, I'm just going to start up here. 1, 2. Put in 1, I get 1. Put in 2, I get minus 4. Negative 3, so pretty steep and negative. 1, 1. I get 1 minus 2, negative 1. Not as steep, but still negative. How about 1, 0? At 1, 0, I get 1 minus 0. We have a slope of 1. And how about 1, negative 1? I get 1, I end up getting plus 2. We have a slope of 3, really steep. Quite a bit steeper. How about 0, 2? Put in 0, get out 2. I'm negative 4, very steep and negative. How about 0, 1? 0 minus 2, pretty steep and negative. Aiming down at that. I try to have some target line if I can. At 0, 0, we're 0. That's not always the case. It just was for these three. And at 0, negative 1, we're actually 2. So I'm looking up 2 over 1. I'm aiming up at there. All right, I'm going to go to negative 1, negative 1. I get negative 1 plus 2, 1. Aiming right here. At negative 1, 0, I get negative 1. Aiming right there. At negative 1, 1, I get negative 1, negative 2, negative 3. Aiming down below. Pretty steep. And at negative 1, 2, I get negative 1 minus 4. Very steep. We aiming way down. Will be 1, 2, 3, 4, way down into here. Okay. And that's supposed to tell us if we had a point on here somewhere and we knew where it was, let's say we were right here, that's going to tell me, hey, I'm trying to funnel down this way, but I'm starting to enter this zone. I'm starting to enter where it wants to flatten off. I don't know if it's going to be right at 0, 0. It may be underneath, but then it's going to try to come back up, and we're getting pinched in here. I don't know. We'd have to investigate later on what's happening, but it's kind of getting pinched in that area. Okay, so here is your assignment on that. I think some of this is going to be very quick. I will say, if it is not very quick for you, please come in and get help. Much of this, other than the tediness of this, we should be able to ramp through in very little time. Good luck. Stay tuned.